So I'm going to apologize. I'll try to freshen it up a little bit, right? But you're going to hear some of that. And I do need to repeat some of the material that we chatted about last time because I need to set up our discussion for today. But I probably will move more quickly through those slides because I know that you're familiar with that stuff, even though the new folks aren't. And I've chatted about it before, but I'll hopefully give a decent enough explanation of those things so that you can follow me when we get to the brand new fresh material. So the fresh material for today, the overarching context for this is climate change, global warming, whatever you want to call it, and how it's impacting the quality of our air. Yesterday, we focused on ozone, ground level ozone, which is a secondary pollutant. I'll talk more about that. Today, I want to focus our attention on particulate matter, or PM as it's often known, and going into some detail on PM, and then how climate change is exacerbating that, and how meteorological conditions impacted by climate change are really exacerbating our air pollution problem with particulate matter. So that's kind of the overarching focus, and we'll get into some other areas today as well. I want to talk a little bit about our recent heat wave, right? I think it was about 2 weeks ago. I mean, I was kind of paying attention to what was going on in the nations in the Great Lakes area when I was getting my talk ready a couple of weeks ago, and I know you guys had some real heat around it. Did it break the 100 degrees? Maybe the heat index, though? Heat index, right? I'm going to talk a little bit about the heat index as well, and it's building here today. Right? When I arrived on Monday, glorious weather, nice and dry, absolutely beautiful. Yesterday, temperatures were creeping up a little bit, and today it's feeling more uncomfortable because of the humidity, and that's because our winds are coming out of the south, right? And they're bringing up some more humidity all the way from the Gulf of Mexico. Yep. So anyway, this is my opening slide that I like to show whenever I'm giving sort of an environmental kind of talk. It gives us context for just about everything else. I teach at UNC Greensboro. I've been there for 27 years in the geography department, but I'm a meteorologist sort of by training and by expertise. But since I'm in a geography program, I've kind of fallen in love with geography. So you're going to get a lot of geography and a lot of meteorology, which kind of explains everything in life from my perspective, right? But we've got some great geography there in front of you, right? I think that the best geography we could sort of have for us, right? Because the planet is perfectly suited to us, right? We have evolved, right, to live perfectly on this planet. It's particularly special, right? You see a whole lot of blue on the planet and some white, so that's our planet's hydrosphere, our water sphere, right? We've got more water on our planet than any other planets in the solar system, right? Right? We used to think we were the only planet with water, but we now know that, at least in the past, there was water on some other planets and entities in our solar system. And I got to remember to use I got a pointer here that I got to remember to use. Usually I'm up on stage pointing at things, but then I'm going to block the view and I'll probably fall off the stage and kill myself. So I'm not going to do that, right? But I much prefer our planet, right? And all the beautiful clouds, and 2/3 of our planet is water, right? Versus this big old rock right over here, right? We're perfectly suited to live on planet Earth. A little theme down here, same theme as from last time. That's going to be kind of continue throughout our presentation, right? Climate change is just making everything worse. Right? So, continuing the theme of how perfect our planet is, there is no place like home, right? However, we're kind of mucking things up. We're doing a good job at that. All sorts of environmental problems, in part related to climate change, exacerbated by climate change, right? A lot of attention is given to more severe weather these days, right? So we got a lovely hurricane right here. I'm not sure. This might be Hurricane Andrew that really whopped Florida many, many years ago now. There's a classic guy, right? But so more frequent severe weather, right, and more intense severe weather. I mentioned on Tuesday that there's a tropical system, hurricane moving through the Caribbean, impacting, I think it's Haiti today. Anybody remember, know the name? Yeah, Beryl, right? So it was a Cat 5 hurricane. It's weakened a little bit because the upper level winds are a little less conducive to Beryl's intensity right now. Plus it's moving over land, right? So it's losing its source of energy, which is warm ocean water. It likely will intensify again when it goes over that big, giant, dirty bathtub that we kind of know as, well, the western part of the Caribbean and the Gulf of Mexico as well, right? But I mentioned this last time. It is so just kind of with the theme of weather is more severe and more frequent. It was a Category 5 hurricane. This is the earliest in the season that we've ever seen a Category 5 hurricane in the Atlantic Ocean, right? So all sorts of firsts with climate change. But so yeah, more intense weather systems, more frequent weather systems, and of course we're worried about sea level rise and with the warming oceans, melting sea ice, and melting glaciers on the land, and our massive ice sheets. Biggest ice sheet, anybody know what the biggest ice sheet is on the planet, where we find that? By far, it's the biggest ice sheet. Antarctica. It's the biggest, right? Next up is Greenland, but that pales in comparison, right? Of course, we're concerned the ice sheet on Antarctica melting more quickly than the worst case scenarios that scientists could envision a while ago. So that's getting a lot of attention. And then, of course, we're worried about biodiversity. Poor polar bear, right? They hunt from sea ice, right? So this is also kind of a theme that you'll see throughout my presentation, right? For the longest time with respect to climate change and associated problems like air quality issues, our head has been in the sand. Kind of is still there with respect to policymakers. Solutions for climate change, easy. We know exactly what we need to do, right? But it's enacting that policy, right? It makes things more challenging these days. So climate change, we talked about heat waves, right? So this is back in June. This is from the New York Times. So I think this was maybe probably the same heat wave that you folks were experiencing, right? So record heat throughout the southeastern U.S., of course, where it's yellow, that's warmest temperatures. And then in the southwestern U.S., some heat already this year, right? So instances of heat. And they used it back when you guys had heard or experiencing your heat wave a couple weeks ago or so. They were using this term heat dome. Did anybody hear any of that in the news? Right? All sorts of, so the media kind of creates some of these new terms, and then sometimes the National Weather Service will sort of pick up on this. And so they're starting to use the term heat dome. And I'm going to explain exactly what a heat dome is later on in the presentation. I didn't chat about that last time, so it'll be some fresh material for you folks. So I mentioned this last time as well, right? So besides warmer temperatures, the seasons are off now, right? Spring is arriving sooner. Summer's lasting longer, and so we need to adjust to that. So this is the dog days of summer are here, and early in New York City is finding some ways to adapt, right? So all part of climate change. But again, the focus of today's talk is climate change, global warming, and how it's impacting particulate pollution or PM pollution. So that's gonna be the focus of our talk today. Want to briefly, and I talked about this last time, make sure that we're clear on the distinction between weather and climate, because sometimes folks get that little bit confused. Invariably, when I'm giving a talk somewhere, someone will mention, let's say that the prior summer was cooler than average. Someone will mention, yeah, but this summer was cooler than average. It was, downright cold for us a bunch of days or whatnot, so there's nothing to this climate change, right? Well, that's weather, right? Not climate. So there's our definition of weather, although, where's that gentleman that shared, he heard this, thank you. So I'm gonna go, I'm attributing it to you though, right? So this gentleman heard this, who'd you hear that from? Some science show, right? On the science show, they said that weather is what you get, right? Whereas climate is statistics. And I like that. That's kind of a good way of thinking about that, right? Here's, maybe a fancier definition of weather, right? The condition of the atmosphere, the condition of these sorts of things right here, the temperature of the air, atmospheric pressure, humidity, the amount of water vapor in the air, right? The amount of cloud cover, the kind of clouds, the winds, and by that we mean wind direction and how strong the wind is, kind of precipitation, how much precipitation, visibility, how far you can see the horizontal, right? Well, all of those sorts of things, right, at a given point in time, a short time frame, right? You get a weather forecast for, well, you're interested in a weather forecast for typically what? Maybe like later today, I was taking a look at I'm a meteorologist, so I was taking a look at some weather maps and trying to come up with a good forecast here. Right, so maybe a day, maybe a couple of days, maybe 3 days or 4 days. But beyond 5 days, forecasts become less accurate, right? But in the short term, they're pretty darn good, right? And generally, we're talking about a smaller geographic area, like for Lakeside, Ohio, or maybe this this general area, this part of the state, or maybe the Cleveland metro area, right? Smaller geographic area, right? Yeah, and we can see, whether at a particular place, at a particular time, right, on a weather map, right? You can see the fronts and the lows and whatnot, just an example of weather map way back from, April 26, right? Weather maps are all used to seeing. So the here and now state of the atmosphere. Climate, we're talking about the same variables or parameters, right? But over a much longer time frame, right? And generally a larger geographic area. For example, I live in North Carolina, which is in southeastern U.S., right? That region. And we can generally expect in the summer, right? Well, what kind of conditions do you think you might expect in the summer in the southeast most days? Any thoughts on that? If you've been to the southeast, North Carolina, South Carolina, Mississippi, Alabama, what's going to be most days? Humid as heck. Right? I know it doesn't generally. You can get some good humid days like today around here, right? But generally, it's not as humid in this part of the country, right? And when it gets really humid here, you folks are generally miserable, right? Because you're just not used to it, right? But it's humid, and we'll get some afternoon thunderstorms most days in the summer, right? Versus the desert southwest, the southwestern area, that region, hot but dry, right? So that's climate by regions and a long period of time. The official period of record for climate that the National Weather Service uses, it's a 30-year record at least. It's trends, statistics, as we talked about earlier. So you can't just take any 1 year or a couple of years. You got to take a long period of time and see where the trend is. Because you're going to get some ups and some downs, but what's that trend line? So I just like to mention that, right? So we're all clear on that. And just, this is just global average temperatures, right? So global average temperatures, long period of time, at least 30 years. And you can see, where we got the orange and the red, that's where it's warmer, and that tends to be in the equatorial area. And interestingly, and these are temperatures in degrees Celsius, where do you see the absolute warmest temperature? Just kind of an aside, but I love maps like this. Where do you see the absolute warmest temperatures? Do you see them over the water or the land? Over the land, absolutely, right? Because the ocean is much more conservative in terms of temperature. It doesn't get so hot and doesn't get so cold, whereas the land heats up much more quickly. And it mixes a lot better as well. And evaporation is occurring as well. All those factors, right? Anyway, so that's climate, right? And we know now, we've known this for a long period of time, that the warming that we've been seeing, it's from human influence, so-called anthropogenic climate change, right? And I just want to spend a couple minutes, probably more than a couple minutes, on what's driving climate change, just to make sure we're all clear on that, all right? And in a nutshell, I'm going to go into some detail here, but in a nutshell, it's because of the enhancement of the greenhouse effect. That's really what we're doing. We're enhancing the so-called greenhouse effect. Anybody heard that term greenhouse effect before? Right? Yeah. So I want to chat about that somewhat briefly. So just reminding everybody, all right, that where do we get our energy for the Earth? Good old sun. Always kind of looking up there, right? That gives us our energy. We sometimes refer to it as insolation, incoming solar radiation, right? Not the pink stuff, insolation, but incoming solar radiation. And here you're just saying, right, I have this up here, right, just to show that, you know, we're getting our energy from the sun. Here we're just seeing the Earth in its 4 key positions as it orbits about the sun, right? So the sun sends us electromagnetic energy, right? And here we're taking a look at a portion of the electromagnetic spectrum. And the sun, oops, sorry about that, the sun sends out most of its energy in this part of the electromagnetic spectrum. Most of it in the visible part of the electromagnetic spectrum, right? At a peak, the sun has a peak of emission of around 0.5 millionths of a meter, right? And one of the ways that we can categorize electromagnetic radiation is according to its wavelength. So, which is why you can see down here, you know, we're showing a wavelength, right? Just like ocean waves, right? It has a peak and a trough and a peak. Well, the sun emits most of its energy right about here at shorter wavelengths. The distance between one ridge, right, one peak, and the adjacent peak is relatively short. So we say the sun emits shortwave electromagnetic radiation, right? In contrast, the Earth, the solid Earth, what you can jump up and down on, along with the atmosphere that, of course, is affixed to the Earth, right? We call that the Earth-atmosphere system, and everything on and in the Earth-atmosphere system emits at much longer wavelengths, at around, I'll throw a number at you, at around 10 micrometers. Right? So the Earth-atmosphere system emits at long wavelengths, the sun at short wavelengths. You gotta keep that sort of in your memory bank. That's a key idea as we talk about the greenhouse effect. Just to try to drive this point home about how the sun emits with a great intensity, right? But at short wavelengths, here you're seeing a graph that shows you wavelength in micrometers versus intensity of sunlight, solar radiation, insolation, incoming solar radiation. And you can see its wavelength of peak emission is way the heck up here. So really intense, but at short wavelengths. Sun at short wavelengths and really intense. But yeah, I mean, you get a sense for that when you're out on a cloudless day, right? On the summer solstice, as an example, right? When the sun is as close to directly overhead as it's going to be here in the northern hemisphere, right? Really intense. Right? In contrast, that's the electromagnetic radiation sent out by everything in the Earth-atmosphere system, right? And you can see its intensity, bless its heart, way down here, not particularly intense, and its peak emission, right, at 10 micrometers, a much longer wavelength. Okay? So sun short wavelengths, Earth-atmosphere system at longer wavelengths. Oh, and just as an aside, what determines the wavelength and the intensity that an object emits at, sends forth electromagnetic radiation, it's the temperature of the object. The hotter the object, the more intense the radiant energy, and the shorter the wavelength. So the sun, it's a little bit warm, right? But like 10,000 degrees Celsius or something, I can't remember numbers, right? But it's pretty hot. So really short wavelengths, right, and really intense. Earth-atmosphere system, the average temperature, well, this was the average temperature of the Earth-atmosphere system, 59 degrees Fahrenheit. All right, a lot cooler, so the Earth-atmosphere system emits at longer wavelengths and a lot less intense, which is, I mean, that's good for us, right? Otherwise, you'd be frying one another right here, right? You'd be zapping, you know, you'd be incinerated. Okay, sun short wave, Earth-atmosphere system, long wave. Plays a big, big role in the greenhouse effect, which is what I'm building to before we get to particulate pollution. Okay, so I suspect most of you are familiar with these gases, right? You probably know them by, I'm using the term here, selective absorbers. You probably know them by a different term, right? And what would that term be? Right? The greenhouse gases, right? The greenhouse gases, right? But a better term is selective absorbers, right? And so we got carbon dioxide, which is sort of like, I don't know, if you had wanted posters of the greenhouse gases, right? CO2 would be, the top wanted poster, right? But there are others like water vapor, nitrous oxide, methane, and ozone, right? Which is both a greenhouse gas and also it's an air pollutant. Plus we've got ozone in the stratosphere as well. I'm going to get to that a little bit later on. Okay, so it turns out, this is kind of like an important bottom line down here, right? These gases, right, they are poor absorbers of shortwave radiation, so energy coming in from the sun, right? But good absorbers of long-wave radiation that is leaving the Earth. Right? So, I had this discussion last time. Right? If we're going to understand this, I need to discuss what can happen to sunlight when it strikes any object. So you can kind of picture here, you got the I'm looking up here, pretending that the ceiling's not here, right? So you got our sun up there, no clouds in the way. The sun is shining through space, then entering our atmosphere, coming down toward the surface of the Earth, and it encounters some object, some particle in the air or some gas in the air. So there are just three things that can happen as that sunlight encounters some object. So one of the three things, right, is that sunlight can be transmitted, pass right through that object, like any of these gases. Pass right through it. Kind of like sunlight moving through a body of water, right? And as you go deeper in that body of water, you can still see some light, right? So that sunlight is being transmitted through that water. When it's transmitted through that object doesn't get heated up. Right? So that's one possibility. And it turns out that these gases, along with our two primary gases in the atmosphere, anybody know the two primary gases in the atmosphere? The two predominant by far gases in the atmosphere. So when you, oxygen and nitrogen. And I can't remember a lot of numbers, but I can remember that the ratio of nitrogen is 78% and oxygen 21%, which is pretty darn close to 99%, right? But those two gases, along with these gases, sunlight passes right through these gases and they don't get heated up. So the sun's coming down through the atmosphere on the way toward the surface of the Earth. Okay? So that's one possibility, transmission through, which is what happens to shortwave radiation. Transmitted right through, and they don't get heated up. Right? The other possibility is that when light encounters some object, like some of these gases, it can bounce right off of them. Reflection. Right? Like when light hits a mirror, or when light encounters like a snow surface. You know, on a sunny day, you look at the snow. Don't see that much of that around here, and even less in North Carolina these days, right? But on a sunny day, you need sunglasses, right? Because that sunlight's reflecting off that snow, right? So with reflection, no heating either. The only way an object gets heated up is when the object absorbs that sunlight. But I mean, you kind of know that, and this is kind of an example in class when I'm talking about this, how some objects, right, like gases and other surfaces, are really good at absorption. So here's my little example that I use with students. I'll say, consider that it, and I'll use North Carolina because it gets ungodly hot in July and August, but I kind of embrace it now, right? It happens to be a cloud-free day, and it's at noon when the sun is most directly overhead. And we're talking, June, July, or August. And you realize that you're out of something that you desperately need, so you decide you're going to go to Walmart because it's going to be cheaper there, right? So you get to Walmart, and again, it's high noon. You get to Walmart, and everybody else, and the grandmother is at Walmart. So you get to park in the far reaches of the parking lot, the hinterland of Walmart, right? And then you realize, oh my God, I didn't wear any shoes. Right? So you kind of start to realize, okay, I'm at Walmart, and what's the surface that my car is parking on? It's an asphalt parking lot, right? Jet black. Now, you probably don't want to go barefoot across it, too, because there's all this sorts of nasty kind of stuff anyway. But you really don't want to go through it because what? It's going to be as hot as blazes, right? Because it absorbs really well. Darker colors tend to, right? So there are some gases, right? These gases that absorb not the sunlight, but the longer wave energy that the Earth is emitting, trying to emit that out to space. Right? So these gases don't absorb it at shortwave, but they do at longer wave. And my next slide here gets to that point, tries to make that point. This graphic does. So on the left-hand side, the yellow, right, wavy lines, that's energy coming from the sun, shortwave energy, right? You can see sort of the short little waves there, or the short wavelength waves, right? So that sunlight is passing through all the gases in the atmosphere, including those selective absorbers, right? Carbon dioxide, water vapor, nitrous oxide, ozone, etc., right? And it reaches the surface of the Earth and gets absorbed pretty well at the surface of the Earth. Most Earth materials are very good at absorbing, so they heat up really well. So the ground, right, now we're over to this slide of the figure, the right-hand side where we got the red wavy lines. So the ground gets heated up, it's emitting electromagnetic radiation, but at longer wavelengths, right? And so you can see that energy at longer wavelengths, these waves kind of going in all directions, some of it down, some of it sideways, some of it up. Now, the greenhouse gases that we just looked at, carbon dioxide, water vapor, nitrous oxide, methane, and ozone, while they let the sunlight in, they absorb the long wave, and they get heated up. So that's the greenhouse effect, right? And thank goodness for the greenhouse effect, right? Because if we didn't have it, the Earth would have an average temperature, global average temperature of around 0, right? Which would kind of shake things up for, for us and everything else on the Earth. So thank goodness for that greenhouse effect. And we have known about this forever, right? The greenhouse effect, right? But what we're doing, right, is we're enhancing the greenhouse effect because what are we doing? We are emitting more and more of these greenhouse gases or selective absorbers into the atmosphere. I mean, there is, room in the atmosphere, right? There are holes where you don't have these greenhouse gases, but when we burn more fossil fuels and through other human activities, adding more of these gases. I made the analogy last time, is like throwing on an extra blanket in bed. Right? I mentioned last time, right? You put a blanket on you at night, generally you haven't warmed that blanket up. I mean, maybe you threw it in the clothes dryer first, but probably not, right? That blanket isn't any warmer than you are, right? What the blanket is doing is it's absorbing your long wave, right? And if that one blanket isn't enough because maybe it's got some holes in it or it's a little bit thin, throw in another blanket. It's like adding more greenhouse gases. So that's the greenhouse effect and how we're enhancing the greenhouse effect, right? And we're going to see how that relates to the enhancement of the greenhouse effect to more particulate pollution. We talked about last time how it's exacerbating our ground level ozone. Today, how it's enhancing the amount of particulate pollution in the atmosphere. All right, just a quick slide here. So just showing you the trend in greenhouse gases. The top slide over here is showing you how CO2 in particular has been emitted at greater amounts since about 1000 AD, right? And you can see that things are really trending up around, what is that, like right around early 1800s or something like that, right? And what do you attribute that to? Big increase in greenhouse gas, in CO2 rather. Yeah, burning fossil fuels, right? Great guns with coal, and now petroleum and natural gas, right? And you can see, yep, that's a rather sharp trend increase in CO2.
Today, CO2 is around 440
It is, and absolutely. And we haven't seen the levels of CO2 in the atmosphere like this, never during human activity, right? This is unprecedented, right? Haven't seen these levels in the atmosphere since the time of the dinosaurs, right? So we're we're conducting, folks make the analogy, we're conducting an uncontrolled experiment on the planet, right? And consequences, not exactly sure how it's going to work out. A slide here on the bottom just shows you that there's a good correlation. It's not a one-to-one correlation between this carbon dioxide that we're emitting and the actual concentration in the atmosphere. Pretty close, right? It's not one-to-one because a goodly amount of CO2 gets dissolved in the oceans. And we are concerned that, and we've seen this in the historical record, there have been periods in the past where CO2 gets released in the atmosphere, right, from the oceans in a rather rapid manner, and that leads to an even more rapid warm-up. So we're kind of concerned that the oceans may be reaching their saturation point. So again, with understanding of the greenhouse effect and how human activity is enhancing it, let's take a look at the consequences of this anthropogenic human-caused warming on the quality of our air. So again, these are the guys that get all the attention, right? More severe hurricanes, more frequent hurricanes, heat waves, and I'm going to talk more about heat waves. We're seeing more wildfires now, right? I'm going to chat about that, but again, focusing our attention on air quality issues, right? So what then are the connections between a warmer planet and air quality? Yeah, it's a complicated scenario, right? Because the Earth's system's complicated, right? One of the challenges for Earth scientists is that, in chemistry, in the lab sciences, right, you can conduct controlled experiments. You can control certain aspects, right, to see how things change. It's really hard to conduct controlled experiments on Earth, in our Earth-atmosphere system, right, because everything interacts. Makes it very, very challenging to hold some variables constant and, see what the consequences are. Okay. So if we're going to understand how air quality is being impacted by climate change, we need to understand a few aspects, characteristics of our atmosphere, right? So when you think about the atmosphere, right, you're kind of looking up, and I'm always, I'm a meteorologist, and so I'm always looking up, and I have to say, my views of the atmosphere here at Lakeside have been pretty special. Last couple night sunsets, whoa. And then you can even see the sunrise, almost see the sunrise, right? You've got a great perspective here, right? Sun rising in the southeast and setting in the southwest. But when you look at the atmosphere, right, you think it goes on forever, right? And that is not the case. Right? We actually define it as a thin envelope of gases, held to the Earth by the force of gravity, kind of like glued to the Earth and rotating with the Earth, right? So it's actually kind of thin, right, and fragile. And it's thin, even though it does extend up to the top of the atmosphere is somewhere like around 480 kilometers, which is way up there, right? But most of the gas in the atmosphere, right, most of the nitrogen and oxygen and these greenhouse gases that we chatted about, right, they're actually held very close to the Earth, right? And that's because gravity, right, is tugging down on these gases, kind of glues them close to the surface of the Earth. And that's, what this slide here is getting to. For perspective, there's Mount Everest, right, which is like 24,000 feet tall or something like that. We'll get like 2/3 of the way up Mount Everest, and half of all the gases in the atmosphere are already beneath your feet, right? Which is why when you're climbing Mount Everest or any tall mountain, you need supplemental oxygen, right? So the atmosphere, if all the gases did extend way up high, then you could kind of emit as much pollution as you wanted because it would get diluted, right? Just like, you throw some pollution in a large river, just a little bit of pollution, that's not a problem because it gets spread out. It gets diluted. But that's not how it is in the atmosphere, right? They're kind of trapped close to the surface of the Earth, right? You really, can't dilute it that much. It's kind of like a strong cocktail, right? Okay. This slide also gets to the point that most of the gases in the atmosphere are close to the surface of the Earth. And also, I need to point out in this slide, we will need this information later on when we talk about how meteorological factors of the atmosphere impact air pollution. Let me just kind of stress that again. So what we put in the air impacts, of course, the amount of air pollution and the kind of air pollution, right? Oh, if it were that simple, right? Because we also have to understand how meteorological scenarios, high and low pressure systems and inversions, and geography, like valleys and mountains, can either exacerbate air pollution problems, right, or lessen them. So you can't just talk about the pollution, right? You also have to talk about the meteorological scenarios as well, and I'm going to get to that later on. That's probably my favorite topic because, again, I'm a meteorologist, right? But what we're seeing here is bottom of the graph over yonder. Oops, there we go. My cursor kind of fades out over here, right? So as we go to the right on this, along the bottom of this figure, we see warmer temperatures, right? So colder temperatures to the left, and we're kind of going up in the atmosphere. Well, this red line is showing you the average behavior of temperature with height. And so you can see how is temperature behaving in this lowest most layer known as the troposphere. It's decreasing on average with height. We call that the lapse rate, temperature lapsing, falling off as you go up in the atmosphere. And the actual average lapse rate, whoops, do I have that word? Don't have that slide yet, going to come to that later on. It's 3.5 degrees Fahrenheit. Really don't need this number, but I'm throwing it at you because it's a number I can remember. For every 1,000 feet you go up, the atmosphere cools off by 3.5 degrees Fahrenheit. Which is why, as you go up, climb a mountain, not only do you need supplemental oxygen because there's less air, it gets colder. You need to throw on a coat, right? So those mountain climbers, right, they're always got their, oxygen, supplemental oxygen, and they're always putting on more special gear. So the temperature decreases with height in this lowest most layer, the troposphere. We call it the weathersphere, because this is where all weather occurs, because this is where all the gases are, right? In this lowest most layer, like 10 to 12 kilometers, right? It's kind of like, lowering. This is a pretty high ceiling here, right? It would be like lowering this ceiling. Okay, so bottom line is, yeah, the atmosphere is not all that extensive. It's thin, and that makes it fragile with respect to human activity. So, yep, we are indeed changing the composition of the atmosphere, right, by adding greenhouse gases and various pollutants, various anthropogenic factors. I mentioned this last time. So we often focus on how humans pollute the air. We're good at it. We got that down. You know who's even better? Mother Nature. She's actually dirtier, right, than we are. It's more pollution. I don't want to call Mother Nature dirty, right? Through things like, oh, there's a good volcanic eruption. I think this might be from somewhere in Iceland. And just as an aside, since I mentioned Iceland, anyone been to Iceland? Have you had the pleasure? Two folks. What did you think? Yeah, yeah. Did you do the, how long were you in Iceland? Okay. Okay. Oh, very different then. No tourism back then. Wow. How long ago did you go to Iceland? 3 years ago. How long were you there? Did you do just the ring road around Reykjavik, or did you do the whole whole ring road around the whole island? Yeah, fabulous. You get a chance, fabulous landscapes. Just sort of otherworldly sorts of landscapes, and get there. Yeah, you're going to say.
Last fall, cruise around the island.
Oh, you did. Okay.
Stopped at, I think, every port.
Okay. Yeah, they're taking some cruise ships now, but yeah. Anyway, you know Iceland's the land of fire because of volcanic activity and ice. Right, so beautiful big glaciers that are receding on Iceland as well, just like everywhere else on the planet, right? And all sorts of volcanic activity, right? So volcanoes, right? And you might know that this is how we got our atmosphere, right? In the Earth's early history, right? We got our atmosphere through volcanic eruptions. Got various gases, including water vapor, through volcanic activity. Much more volcanic activity in the early Earth. Anyway, these are all natural sources of air pollution, right? And you're going to see many of these, if not all of them, when we take a look at human-produced air pollution, so-called anthropogenic air pollution, right? So anyway, in Mother Nature, I mentioned she's dirtier, right? In the sense that she produces more air pollution than we do. It is just that Mother Nature, she's got her act down. She does it better than we do in the sense that she spreads it out over the whole globe, right? And if you do that, then the air can, for the most part, right, can dilute that pollution. Whereas humans, where do we tend to be concentrated? Where do we tend to live? And this trend is, ever increasing. Urban areas, right? Folks are moving to urban areas. So a lot of people and a lot of stuff that they are doing, so a lot of pollution in a small geographic area, which makes it really hard for the atmosphere to dilute, and particularly under certain meteorological conditions, like inversions, which we'll get to, right? Anyway, these are all the natural sources, right? So from volcanoes, we got SOx, oxides of sulfur, particles, right, or particulates, PM matter as we like to call it, forest fires, right? More and more wildfires, right? Remember last summer's wildfires, brutal in the northeastern U.S. and even mid-Atlantic and the southeastern U.S. And I know you experienced the forest fires, the effects of the forest fires here on air quality. Plants even emit pollution, hydrocarbons. So hydrocarbons, sometimes called volatile organic compounds. It's hydrogen and carbon. It's, as an example, petroleum, right? Gasoline, petroleum as an example. That's what hydrocarbons are, right? Hydrogen sulfide, even soil, right? Dust and viruses as an example. Natural sources, right? And these are anthropogenic air pollutants here. So you can see many of these same pollutants. And I sort of see a theme in this list of pollutants. And actually, I say this little asterisk denotes that the above pollutant results from the combustion of fossil fuel in transportation and at power plants and factories. Actually, each of these should have an asterisk. When I was making the slide, I forgot to put some asterisks. So all of these, the theme is they're all associated with the combustion of fossil fuels. Right? Okay. So just talking a little bit about how we classify air pollution in order to understand the different kinds of air pollution. And again, we talked a little bit about this last time. So we've got primary pollutants, right? And they're emitted directly from an identifiable source. So they come out of the tailpipe of your car, or out of that smokestack at the power plant, right? Or out of the tailpipe of a big bus or whatnot, emitted immediately into the air and pollutes the air, right? The other class of pollutants, and here are our key primary pollutants, right? So you got carbon monoxide, right, 58%, right? Nitrogen oxides, sulfur oxides, and when you think sulfur oxides, think coal, right? Sulfur is a byproduct of coal, right? And some forms of coal, the cheaper coal tends to have a higher sulfur content, right? There are volatile organic compounds, 11%. And again, we use the term volatile organic compounds and hydrocarbons interchangeably. And then what we're focusing our attention on today, this particulate matter, right, 4%. But it's an important 4% because it has a huge impact on health that we're just now understanding. Kind of took it for granted for a long period of time. Didn't even monitor it for a long period of time, but we now realize that health-wise, it's really, really significant, right? That PM, that particulate matter. And where do these primary sources come from? Transportation, right? Which is why, folks at the Environmental Protection Agency harp on making our sources, our forms of transportation cleaner, because that's a big chunk of the primary pollutants. So it's kind of like low-hanging fruit for trying to clean up our air. So that primary pollutants. Another class of pollutants, secondary pollutants. So they don't come right out of the power plant, the smokestack, or out of your tailpipe, right? They form just a little bit later on, like almost instantaneously, right? from the interaction of various primary pollutants. So are not emitted directly into the air, but form in the atmosphere when reactions take place among the primary pollutants. And ozone is our most, ground level ozone is our most problematic secondary pollutant. Little graph here just illustrating the secondary pollutants and the primary pollutants. So you can see cars and vans and whatnot on the road, and you can see some smoke, right? Exhaust coming out of their tailpipes. And we've got a sunny day here. We chatted last time about how ozone has a season, right? You only make ozone when you have strong sunlight, so it's only during the hot part of the, during the summer season. And it's only from roughly, different states start their monitoring at different times. I think here in this area they start monitoring in April, and it continues through November because temperatures are warm enough during that period and there's strong enough sunlight. So you need that to make ozone, right? So anyway, you got the exhaust coming out of the tailpipes, right? And it goes up into the atmosphere near ground level, and it's all kind of mixing together. All sorts of chemical reactions are going on in the presence of strong sunlight. And then over here, you make things like ozone, right, and pan, right? So these are secondary pollutants, right? And again, ozone was one of them. We're going to see that particulate pollution can be a primary pollutant, and it also can be a secondary pollutant. It's secondary forms of particulate matter that are really the most challenging and dangerous, because they tend to be the finest, the most inhalable into your lungs, easiest inhalable. Just a couple of the classifications of air pollution, a few more terms for you. So you're probably familiar with the term smog. I thought you might be curious as to the derivation, right? And when you think smog, you often think of scenes like this, right? This is the old classic industrial smog where visibility is significantly lessened. So this is London, 1952, and they had to have the street lights on during the day because there was a lot of smoke, a lot of particulate pollution, and fog. Water in the atmosphere, in the gaseous form, and also in the liquid form, is very attractive to certain pollutants. They kind of want to form on those, either gaseous water or on the liquid water droplets. So it can enhance air pollution when you have a lot of water vapor in the air. And you might have noticed on a more humid day, visibilities are impacted. Look out over the lake on a more humid day, right? You can't see as far. If you go into the mountains on a more humid day, right, and you've got air pollution present, tends to be a whole lot hazier. I hail from North Carolina, do a lot of hiking in the Great Smokies. Anybody had a chance to spend any time in the Great Smokies? Maybe you've been in Asheville, North Carolina, which is sort of like our most well-known city. Asheville is just glorious. Great Smoky National Park, it's the most visited national park in the country because its proximity to major metropolitan areas. Also has the poorest air quality in terms of particulates and in terms of ozone, in part because of the high humidity and in part because of its neighbors to the west. So Virginia and you guys as well. Have you ever flown across, from let's say your neck of the woods here to the eastern seaboard on a clear day and look down below? What do you see? It's a sea of power plants, big, tall smokestacks. And when the wind direction is right, your pollution and West Virginia's pollution, right, and our pollution, right, all kinds of hang out in the Great Smokies. So it's problematic right there. So this is kind of the classic example of the smog. We've actually done a pretty good job at cleaning up this old form of pollution because a lot of it comes from power plants, and now with scrubbers, right, and regulations on what the kind of coal they can burn, and they're shifting to natural gas. This kind of pollution, so-called old industrial pollution or industrial smog, is less problematic, right? Another kind of pollution is known as photochemical smog, and ozone fits in that category. It's a secondary pollutant. It's also a photochemical pollutant, and the term is helpful, right? Photosunlight and chemistry. So it forms through all sorts of chemical reactions and sort of the two infamous forms of photochemical smog, nitrogen dioxide and ozone. Ozone is actually invisible, tasteless, and odorless. Not the case for nitrogen dioxide. And if you've ever flown into any major metropolitan area, I always think of LA because it's kind of famous for this kind of smog. You're way up high in the jet and you're coming down, you know, you're starting your approach into the airport, and as you get down below the blue skies, you know, you start to see, you know, sort of this haze and yuck. Most of that is from nitrogen dioxide. It is not invisible or odorless. Just going to quickly through this because we focused on ozone last time. But anyway, this is how you make ozone. It's complicated as heck. There's a lot of fancy atmospheric chemistry going on, but essentially what you need strong sunlight. So that's why ozone is only a problem during the summer season, right? And then you need some primary pollutants, nitrogen oxides, right, along with some hydrocarbons. And both of these, the oxides of nitrogen and the volatile organic compounds, are emitted from cars, buses, and trucks. And when you fuel your car, right, and voila, that makes ozone. So these pollutants kind of bake together in direct sunlight. Right? Don't have to worry about ozone during the low sun season, which would be the winter season. So as we get into late fall, in winter, they don't even monitor for ozone because it's not problematic. Temperatures aren't high enough, and you don't have strong enough sunlight. Okay, on to particulate matter. All right. So PM, it's a term for a mixture of solid particles and liquid droplets. We sometimes use the term aerosols. Right. So particulates, aerosols, whatever term you want to use, little teeny liquid droplets. Right. So much smaller than a raindrop, though. You know, when you might be mist your plants, kind of sometimes you mist your plants, certain kind of plants, I guess it's good to mist them or mist, M-I-S-T, mist them or whatnot, and that fine spray comes out, those water droplets, those are much larger than our aerosols or particulates. They're very, 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 very small, sometimes microscopic, right? So it's this mixture of solid particles and liquid droplets found in the air. So some of the particles, some of the PM can be dust, right? Kicked up from human activities like road building, right? Or any kind of construction, right? Where you're disturbing the soil, right? Dust, dirt, soot from power plants, from chimneys, as an example, all right? Those are all sources of PM. And some of this you can see, the larger stuff, larger PM, you can see with the naked eye. Others, and the kind we're most concerned with respect to health, right, can only be seen using an electron microscope as an example. So you got two classes, right? The Environmental Protection Agency, who is responsible for enforcing air quality regulations, right, are concerned with these two classes of particulate matter, so-called PM10, right, that have diameters of generally 10 micrometers or smaller, and the largest stuff you can see, or the PM2.5. And I mentioned this last time, the federal governments, the EPA, they established the regulations, right? How much PM10 can be emitted, how much PM2.5 can be emitted, right? But the states are actually responsible for monitoring. It's their job to monitor air quality levels. And some states do a better job than other states. You guys do a really good job around here. I did my PhD up in Wisconsin. They did a really good job there as well. So the Great Lakes region, the upper Midwest, an excellent job. Northeastern U.S. does a really good job as well. Mid-Atlantic states, Southeast, not so good. They've been behind the curve. North Carolina's not too bad. When you get to some of the more southern states, the EPA has to use they use a carrot and a stick sort of thing, right? They can use highway funds as kind of a stick of highway funds if folks don't come up with a good plan to meet air quality standards. So PM 2.5, though, that's what that's what they're most concerned about, because they are the finest. And your lungs and your nose and all those sorts of things, right, they don't filter out the PM 2.5. So deep into your lungs, right? And so that's 2.5 micrometers. We sometimes use the term microns, or smaller. So for perspective, how small is 2.5 micrometers? Well, think about a single human hair on your head. The average human hair is about 70 micrometers, right? So that's 30 times larger than the largest fine particle. Here's a little figure, just giving you a point of comparison. So good old beach sand, right? That's about 90 micrometers, microns, so pretty large stuff. Human hair, 50 to 70. Even dust, pollen, and mold, right? Which is, PM, right? That's getting small, less than 10 micrometers, but they're really fine stuff. Combustion particles, so from fossil fuels, right? Power plants, but other forms of industry, right? Organic compounds, metals, etc. So from industrial sorts of processes, right? And you breathe that deeply into your lungs. And again, this is really maybe over the last just 10 or maybe 15 years that studies have shown that this is the PM 2.5, the really insidious stuff. So sources of particulate matter, right? They can be emitted directly, so they can be a primary pollutant. They can be emitted directly from a source, construction sites, unpaved roads, fields, smokestacks, or fires, right? Yep, so fires are a source of PM as well, wildfires. And we're seeing more of that now, right? From climate change, right? Most, though, PM form from complex reactions of chemicals such as sulfur dioxide and nitrogen oxides from power plants, industry, and from automobiles, right? That's the finest stuff, okay? So, again, it's the fine stuff, the 2.5, that we're most concerned with. What are the health effects, right? So premature death in people with heart and lung disease. So the theme is, with most air pollution, it's the young folks, right? So children and the elderly and folks that have a pre-existing health condition, lung issues or cardiac issues that are most at risk, right? And they didn't used to be so concerned with healthy individuals, but we now know, with respect to just about all pollutants, ozone and PM, that even healthy folks that are exercising vigorously, right? So sports teams, college football teams or baseball teams, they're outside, practicing hard, or folks outside doing construction work, right? Are impacted as well. So sort of long-term, exposure is problematic. Anyway, non-fatal heart attacks, irregular heartbeat, aggravated asthma, decreased lung function, increased respiratory problems, right? And this kind of gets to a social equity, right? Climate justice sort of issue, right? It's the folks in inner cities, right, that have less access to filtering devices, air conditioning in their home. They're close to transit stations, close to more industrial sites. They're greatly impacted by PM. So a lot of research has been done in these sorts of neighborhoods, and it's very clear that the health consequences there are much more significant. Plus, there's a whole economic aspect of this, right? It impacts visibility. When people go to the mountains or they go to the Great Lakes, right, you want to see these big, beautiful vistas. You want to be able to see forever. You want clean air. So it affects, the economy in these places as well. And I mentioned already the Great Smoky Mountains, the most visited national park in the country, right, also has the poorest air quality. So I wanted to spend just a little bit of time chatting about the standards. How much PM is too much PM, according to the Environmental Protection Agency. So these are the so-called the NAAQS, the National Air Quality Standards. So again, it specifies a maximum amount of PM to be present in outdoor air. And I'm not getting into this in this talk, right? But what is outside comes inside. So this impacts indoor air quality as well. Focus is heavily on the 2.5 because that's the finest material. Generally have more health problems with the finest material. It's 9 micrograms, right, or microns per cubic meter. And It's an annual average, and you average it over 3 years. So with respect to most pollutants, they do a longer term average because 1 year can be, deviate from it can be an anomaly because meteorological conditions impact the ability of the atmosphere to dilute air pollution. So maybe you've got a year that's abnormally warm, right? And so you might have higher than average air quality. So they'll go ahead and average it. In this case, over 3 years, trying to normalize things a little bit, and that's standard for most air pollutants. So this is the EPA's Air Quality Index. Maybe you've seen this, easily accessible. Just go to Air Now. I went to Air Now for, the closest monitoring sites I could get were over in the Cleveland area. I don't know if I didn't find any monitors here, but for ozone for us today, we are in the green, right? So it's not a health issue. But for particulate, we're actually in the yellow, in the moderate. And you can see that that's acceptable for most folks, but for the elderly and children, folks with pre-existing health conditions, it can be of concern. The orange area is where we need to get concerned, and generally, if it's a code orange day, that would mean that you are experiencing more than this 9 micrograms per cubic meter. That's kind of where the orange area settles out. This Air Quality Now Index, during the summer season, it takes into account both ozone and particulate matter. So if you're in a code orange, it could be for either ozone or it could be either for particulate, but you can actually kind of drill down into their website and you can see the values for both ozone and particulate, PM 2.5 and PM 10 if you're curious, right? During the non-summer season, they don't monitor for ozone, so what you're seeing is just particulate matter. They monitor particulate year-round. It's not as much of a seasonal, there's a lesser seasonable impact. Just letting you know, so if you want to go ahead and get the air quality index for your area, you can get it for a forecast. They usually do 2 or 3 days in advance. This is just for one I grabbed for North Carolina. So part of the state, the western part of the state was code yellow. The eastern part of the state was code green. Any thoughts on why the eastern part of the state here, and this tends to be kind of typical for North Carolina on most days. Generally, there's poor air quality over the western 2/3 of the state. Generally, better air quality over the eastern. Yeah. Yeah, flatter topography. You also often get a nice sea breeze on certain days. Better ventilation, better mixing, closer to the coastline, and importantly, less industry. Generally, over the eastern part of the state. Charlotte is located, our biggest city, is kind of located down about, oops, I'll find my cursor there, down here in sort of south central North Carolina. And then we got in the central part of the state up here, we got Winston-Salem and Greensboro, and then Raleigh is over here, right? So meteorology plays a role, and so too does your pollutant sources, right? The American Lung Association, they kind of take a look at how we're doing air quality-wise. Do a very good job analyzing air pollution data and coming up with their report card, so to speak. We talked about the report card for ozone last time, so this is going to focus here on the report card for particulate matter. Right? So they do issue, so the report card is based on scores for ozone, year-round particulate pollution, and they also do a short-term particulate pollution as well, looking for spikes in particulate matter. Right? So here is their report card for PM 2.5. Right? So more than 65 million people in America live in counties with an F grade. That would mean that they're generally non-attainment areas, not meeting that value that the EPA specified. So these what's interesting is these counties are disproportionately located in the western U.S. And so it's again the western U.S. that's experiencing is having the most problem attaining that PM standard. And what we're attributing that to is, right, the wildfires in particular, which we know is, wildfires becoming more and more problematic. And it's particularly in the western US because that's where conditions are drier. Winds tend to be higher, so it's harder to put out those wildfires. And there's much more drought going on in the southwestern US, right? And the east of the Mississippi, right, generally, some areas might be experiencing drought, but generally we receive plentiful precipitation east of the Mississippi. So bottom line, climate change is leading, and it's climate change, of course, that's driving the wildfires, right? Drier conditions, more sunshine, hotter temperatures. Climate change is leading to more drought and wildfires, and thus more particulate matter. So it's really the western U.S. that is experiencing this problem. So just a little bit of information here on PM from wildfires and environmental effects. So again, besides the health effects of PM, right, the environment's impacted as well, right? So it can acidify streams and lakes, change the nutrient balance in coastal waters and large river basins, right? Deplete nutrients in the soil, damage sensitive forests and farm crops, right? And affects the diversity of ecosystems as well. So it's not just health effects with the increases in PM, which are again in the western US resulting largely from the wildfires, right? But there also is a trend, maybe this is shifting now, more and more folks moving to the west and southwestern US, although that trend is probably being alleviated. Okay, urban heat island effect. So we got talking about air pollution, right? And we talk about climate change, which is ratcheting up the heat. Well, there are other factors that play a role on a more local scale, more local geographical scale as well. And one of them, and this is getting more and more attention as of late, the so-called urban heat island effect. Sometimes folks will use the UHI, Urban Heat Index. So I wanted to chat a little bit about the urban heat island and what drives warmer than normal temperatures in our urban areas. So in this image, right, it's looking at increasing temperature over here, and we're going from rural area to suburban, right, to the urban core, and then over here back to the suburbs and rural area. And you can see that, yep, it's warmer on average in the urban area, right, versus the surrounding countryside. A clear pattern shown in all urban areas, right? And as we drive up the temperatures, it drives up the conditions that promote greater amounts of air pollution. Ozone, for example, and particulate. So why are urban areas warmer than the surrounding countryside? Urban areas, what do we find in urban areas? Not a whole lot of grass, maybe a few parks, right? If you're lucky, right? It's the concrete jungle. It's asphalt surfaces, right? It's concrete buildings. It's a whole lot of steel that conducts heat from the sun, right? That shore wave coming in gets absorbed by all these materials, gets stored in these materials. Larger amounts get stored before it gets released, right? And so this drives up the temperatures. So you get, the bottom line is you get higher temperatures during the day, higher maxes, right? And higher mins at night. And it's really the mins at night that are most problematic because it's at night where people need to cool off, right? They need to lower their body temperature and get cooler. If they don't get cooled at night, right, and the next day is hot, it leads to health problems. And again, it's the folks in the inner city, right? It's the whole equity issue here. They might not have air conditioning, right? And so they're really susceptible to these higher minimums at night. So some other factors that impact the urban heat island. Urban areas tend to have a lower albedo. It's a synonym for reflectivity. Right? Urban areas tend to reflect less of the sun. Remember the reflection? No heating. If it reflects really well, reflects all that energy, it's not going to get heated up. Like snow, like light bouncing off, sunlight bouncing off of snow or off a mirror, it doesn't get heated up. Well, cities are less reflective, so that makes them more absorptive. Not a real word, but I think we know what I mean. They absorb better, so they get warmer, right? So they have all this energy, right? They're absorbing this energy, they're getting hotter, and they're actually spending that energy in the form of heat that you can sense, that you can feel. We call that sensible heat. Just a quick illustration of albedo, right? So that snow is reflecting the sunlight, so it's not melting, but that leaf, right, is absorbing, so it's warmer, so it's melting that snow, right? So urban areas are more like that leaf. Also, and this is a biggie, right? Cities have a lot of impervious surface. When it rains in an urban area, where does the water go? Storm sewers. Not into the ground because it can't. It's concrete and asphalt, right? It goes into storm sewers, and the water goes right to the lakes and streams. Whereas in a rural area, you got a lot of grass, right? Vegetation that water is going to soak in, right? So you got some water in the surface that can be evaporated. And evaporation is it's a cooling process, right? It takes energy to convert that liquid water that's in the ground to gaseous water, to water vapor. And so there's if you're using that energy from the sun, right, to evaporate water, there's less that can be used to warm up the ground or the overlying air, less sensible heat energy. Right? Evaporation is a cooling process. Right? I douse you with some water now and don't give you a towel. You'll sit there and be mad at me and pretty miserable, right, and get cold because the water is evaporating from your skin. It's going to take energy from your body. So this is a really big factor. That's why when you go into a park, yeah, you've got vegetation, trees, right, blocking the sun, right, but a lot of the cooling is because of the evaporation of the water in the ground. Right? And that's a huge, huge factor in making vegetated areas much cooler than urban areas. Right? It's just a little graphic showing you. So that on the left, we got energy coming in from the sun. How are we going to spend that energy? Well, if you don't have a lot of vegetation around, some's going to go into the ground, but a lot of it's going to be used to heat the surrounding air, call it, again, sensible heat energy. But over here, if you got some vegetation, we're going to be spending some of that energy in evaporating, so less for sensible heat energy. Also, in the city, you got all these weird angles, irregular geometric shapes of cities, so that kind of traps the energy in the city. And then, people live in cities. They drive their vehicles, right? They turn the air conditioners on. There's industry, all of that adds to the urban heat island effect, right? So you got climate change, and then in urban areas, you're adding like another layer of heat, which creates even more air pollution, right? More sunlight, higher temperatures. It's just like wonderful. It's a panacea for getting more dirty air into the air, particularly ozone and particulate matter. So let's see. Oh, so remember in urban areas, the minimum temperatures at night are higher, which is problematic for health. So what compounds that issue and makes the minimum temperatures even higher is that in urban areas, you tend to have more particulate matter in the air over the city. Well, at night, right, you've got the ground emitting long-wave radiation, long-wavelength radiation, into the atmosphere, and that particulate pollution, just like the greenhouse gases, absorbs that long wave, and it keeps the air warmer. The ground, it's like throwing a blanket. That pollution, absorbing the long wave, it's like putting another blanket on the city at night, keeping it even warmer. So, as an example, New York City, its urban heat island index, studies have shown that it's 8.5 degrees warmer than it would be if it were not an urban area. So 8.5 degrees on average. Now that is significant, right? All right, I'm going to kind of skip ahead here so I get to some other things. So I made this analogy last time, right? So, sort of at the start of the Industrial Revolution, or sort of during the middle of the Industrial Revolution, where we're starting to burn fossil fuels, it's like we were living sort of on the bottom floor of a house. With climate change, we've moved to the second story of the house. Remember that heat rises, right? And when you have the urban heat island or some other meteorological factors that I'm going to get into, it's really as if we're living in the attic right now. That's what climate change and some of these other factors is giving us. Okay, so now, it's kind of my favorite part of the talk. Mentioned that, yeah, an important factor is what the emissions are that you're getting into the atmosphere, but the meteorological situation can exacerbate things, can improve or exacerbate the quality of the air. So I want to talk a little bit about some sort of exacerbating factors with respect to air quality. So some good meteorology. So one of the items is a country breeze. So cities are warmer on average, urban heat island effect, right? So what happens is that an area of lower pressure tends to form in urban areas, right? Lower pressure. Whereas we find higher pressure away from the city. So there's like a high pressure area here and a high pressure area here. Well, I always say in my classes that everything kind of flows downhill in nature toward lower values of whatever you're talking about. So when you have air, and you've got an area of higher pressure, which is just where you have more air in a given spot. So more air here, more air above here, high pressure. An area of lower pressure over here where there's simply less air above. What's going to happen? Things are going to flow downhill. Mother Nature really wants to balance things out, right? So what's going to happen is air is going to move from where you got a lot of it, high pressure, to where there's less of it. So since in the middle of the city we develop an area of low pressure because it's warmer there, right? Air blows from the country into the city at night, and what happens there is that tends to bring all that particulate matter, it causes it to rise in the atmosphere and kind of creates this dust dome, which enhances the amount of long wave that the ground is emitting and keeps it even warmer. So you got warmer temperatures, and now you've got even dirtier air. Oh, and we often have industry outside of the city, right? So that pollution from the industry outside of the city is being drawn into the city. So that's that dust dome effect that results from the meteorological situation, right? Just exacerbating everything. Okay, so that's one meteorological factor. These are my favorites here. And then let's talk about stability and inversions. So remember early on when I was talking about the vertical structure of the atmosphere, that most of the atmosphere is held close to the ground in the troposphere, and temperatures on average, as you go from the ground to the top of the troposphere, they decrease on average by 3.5 degrees, 3.5 degrees Fahrenheit per 1,000 feet. So it gets colder with height, right? On average. Well, nothing ever stays average, right? It turns out that there are scenarios, meteorological scenarios, where it can actually get warmer with height at certain levels in the atmosphere. And we call that an inversion. The normal case, the non-inverted case, is it gets colder with height. The inverted case is when it actually gets warmer with height. So that's what we're seeing in this particular graphic. In the top figure over here, we're seeing the usual case, right? It's getting colder with height. Typical scenario. So when you have a power plant, right, here's particulate matter, whatever pollutants coming out of the power plant, right? Remembering that what does warm air always do? It rises. As long as as the air is rising, as long as the air stays warmer than the adjacent air, right, it'll continue to rise. In a home during the winter, you're heating your house, right? It's always warmest up at the ceiling, right? Because that warm air coming out of your heaters rises to the ceiling. That's why you have a ceiling fan, trying to circulate that air. Warm air always rises. So in this scenario, right, because it's getting colder aloft on average, right, and the plumes of smoke are warmer, right, they will continue to rise, right, because they're warmer in the adjacent air, which is great, right, because that's kind of diluting the pollution, spreading higher and higher and higher and not causing you a problem. Here is our inversion. Very typical at night when we have, see the moon, when we have clear skies. Okay, you can actually see that, it's not getting cooler with height, it's actually getting warmer with height, at least near the ground. And that's because the ground cools off more quickly than the overlying air, right? So the ground cools the lower atmosphere, so it's actually getting warmer aloft, right? Until you get up higher, above this ground level inversion. So these, industry and smokestacks over here, right? Since the smokestacks are kind of short, right? The pollution is being emitted below this inversion, right? This inversion kind of acts like a cap, kind of like a ceiling. You know, if I set this side of the room on fire right here, the smoke's going to rise. Well, it can't go any higher than that ceiling, right? It's going to like spread out. Well, that's kind of what's going on over here. Now, this smokestack's above the inversion, so you're fine. But, right, if this is the level of your inversion, then all this gets trapped in the urban areas as well. So you might have this going on, and then you might have the country breeze, you know, exacerbating air quality. So this is where you got to take a look at the meteorological conditions. So to eliminate this problem, ameliorate this problem, when they're building smokestacks, they should build them higher than the average inversion level. And you might notice, just a quick aside, again, if you're flying across, you know, from east to west, west to east or whatnot, and you're flying over parts of Ohio and Western Virginia and Kentucky, you'll see some really tall smokestacks, right? And they've done that for a couple reasons. They're really tall because they've tried to build them high enough above the average inversion level, above the average ceiling level, so that it'll ventilate. Plus, under certain scenarios, right, some of that pollution can mix down to the local adjacent area, and that's not a good thing. So they build it really high so that it gets transported far away. But you know what? Someone's always downwind, right? And because the prevailing wind throughout a good portion of this part of the country is from the southwest to northeast, guess who gets a lot of our pollution from our power plants and has sued us up the wazoo for a number of years? Oh, Canada. And they have won, right? They have won. Okay, so that's stability and the inversion. Okay, here's another example. So that was, this previous one was at night, nocturnal inversion we call it, because the ground cools off more than the overlying atmosphere. This is a result of high pressure systems. So with an area of high pressure, the air sinks, right? And sinking air warms, right? So what's happening when you have an area of high pressure, the air is sinking and warming and creating this inversion right in this particular area right here. See how it's getting warmer with height? That's because of the high pressure and the sinking motion and the warming that's occurring. So this is acting as a ceiling. And this is quite problematic. And this is why when we have large high pressure areas that sit over a region for a long period of time, and you might notice this. So the weather is kind of quiet, lots of good sunshine, and you might hear the meteorologist saying, yeah, it's because there's high pressure, and weather's really good with high pressure. Well, the weather's nice, but the high just sits there, and the air keeps sinking and warming up, and you have this inversion like we had during the recent heat wave, right? And so the air quality gets worse and worse and worse and worse until that high gets jettisoned out by an area of low pressure and a couple of fronts moving through, and then the air will be, with low pressure, the air tends to rise and it cools off, right? So, and we're seeing with climate change, we're seeing more of these stagnant high pressure areas that just sit in an area for a long period of time, and temperatures build up and air quality worsens, and that's also conducive to drying out the land, drying out the vegetation, and to wildfires. And we're definitely seeing that with climate change. So some actual pictures here. So you can see, right, nice clear blue skies. Right, but down here we've got haze. So topography plays a role as well. The air pollution tends to get trapped in valleys. And this is why air pollution is so problematic in LA as an example. You got the mountains, just outside of the LA, and you also have the sea breeze blowing from the sea to the land in LA, so the pollution just keeps getting higher and higher and higher, and often high pressure is present throughout most of the summer in LA. So that's why they have some really nasty air quality episodes in LA, although they're doing much better through strong air quality regulations, right? So we call that a, when the air sinks because of high pressure, we call it a subsidence inversion, and it's worse in valleys. Anyway, I make a little, that's me, and that's my plane. I'm a pilot. That's how I got here. I love to fly. Yeah, this is besides my partner, this is the love of my life. I actually flew to Port Clinton Airport. I got to fly along. I flew from Cleveland to here. Great views of Cedar Point. That was really cool. And just the Lake Erie shoreline. But every summer when I'm not teaching, I try to make I call it my Western pilgrimage. I like to go to the Southwest just because the landscape is so cool. So I've got some images of my Western trip. I think I'm on my way out west here. So anyway, I'm still east of the Mississippi. Very typical scenario. Typical summertime haze east of the Mississippi from particulate pollution. You can see kind of nice blue skies up above, right? But down below, hazy conditions. Very typical from all the pollution from the major urban areas and from all the fossil fuel burning plants. I'm not quite sure what that river is. It might be, I don't want to speculate because I'll probably get it wrong. So Texas, right? This is an example of what an inversion can do. A lot of dust storms, very windy conditions in parts of Texas and the southwestern U.S., so all the dust gets kicked up, but it's trapped below the inversion, high pressure. So you can see down below, you can see that dust. Up above, you can see the inversion. Another picture of the haze east of the Mississippi, but there's some clouds here, but clearer skies above. This is somewhere over West Virginia, I do believe. No inversion, and you can tell whether there's an inversion or not. Take a look at the plumes from the smokestacks. Are they rising? And that's what they're doing here, right? And you can see the air quality is reasonably good here. So maybe a little weak inversion here, but not too bad, right? In contrast, do you see the clear ceiling on the atmosphere there, right? So above, excuse me. So above, right, this is the ceiling right here. Nice clear blue skies. Look at these power plants right here. This again is somewhere in West Virginia where there's power plants everywhere and strip mines everywhere. Right, a clear ceiling right here. And so this, pollution, right, it just stays right here, right? And the pollution gets trapped below. Oops. Let's see, let me go back. I did the same thing last time. I've got a little video, I think, of this next one, if it plays properly. Oops. Okay. So maybe it's not going to play. This is, let's see what happens here. No. Anyway, this is a little video that I inserted, but I'm having some trouble with it. Anyway, this is near Greensboro, North Carolina. And you can see the cumulus clouds. They're building a little bit, and that's an indication. If they got some vertical development, that's an indication that you do not have an inversion. It's going to be a pretty decent air quality day. So some other factors, and I know, I'm getting, thanks, John. Let me see if there's anything desperate that, this is a typical scenario, right? Both topography and meteorology. At night, the ground tends to cool off more than the air in the middle of the valley. So the air adjacent to the ground will get colder. What does cold air do? It sinks. So we call that cold air drainage. So what will happen at night is the air will drain down into the middle of the valley, bring pollution along with it, and you've got a good nocturnal inversion, which acts on the ceiling, and you can get really poor air quality in the valleys. Pardon? That can happen in Denver, right? Very common, too, in a lot of valleys in West Virginia and also in Ohio. I think I am out of time, so I'm just going to, I had other slides to show you, but let me go cut to the final slides. Same slide as last time. I'm going to zip on through here really fast. Don't look at any of this. Yeah, I almost finished everything. So what we've been doing with respect to global warming, showed the same slide last time, so I apologize, right? For the longest period of time, we have been burying our heads in the sand, and we're kind of starting to pick them up a little bit. At least policymakers are. Not quite there yet, right? Hopefully we'll do that before it's too late because there's no place like home. All right, hey, thanks very much. I appreciate it. And to those that came to both sessions, bless your hearts. I appreciate it. You're troopers. If I had a door prize, I'd give you one, but I don't. Have a great day, and thanks for your hospitality.